So we're going to problem number 3 of this series on almost impossible integrals, sums, and series. And this problem consists of 4 integrals. One is I to the n, which is equals to the definite integral from x equals to 0 to x equals to 1 of x to the power n minus 1 times the natural logarithm of 1 minus x. And then Jn, which is a definite integral instead of what we had with In. This is a definite integral from x equals 0 to 1 of x to the n minus 1 times the square of the natural logarithm of 1 minus x. And Kn now takes this natural logarithm to be cubed, and Ln is the natural logarithm to the fourth. So we're going to see how these integrals are related to one another, but at the far end of it all, we want to see how these integrals are also related to what we call the harmonic series. So that's going to be our focus this time around. These are very interesting integrals. And for those of you who like calculus, you might actually find this to be interesting. Without much ado, I'd like to encourage those of us who haven't subscribed to our channel to please consider subscribing to our channel. That support that you give us will go a long way in increasing our profile. But also, if you like what you see, please just stop for a minute and like our video. Also share if you can. Your support is going to be much appreciated. So let's move forward to solve these problems one at a time. So let's begin with In, right? In being equal to the definite integral from x equals to 0 to x equals to 1 of x to the n minus 1 times the natural logarithm of 1 minus x. So that's our integral, right? And this part here can be expressed as the derivative of x to the n minus 1 over n, right? Then we can use integration by parts, which for those of us who don't know, is that if you have an integral of a product of a function v and a derivative of a function u, when you integrate that, you get the product of u and v minus u times the derivative of a function v. So with that in mind, what do we do next? We consider this part to be u and this part to be v. So what is our uv? Our uv becomes 1 over n x to the n minus 1 natural logarithm of 1 minus x from 0 to 1 minus our u is going to be here, so we have integral from 0 to 1 of 1 over n x to the n minus 1 times the derivative of the natural logarithm of 1 minus x. So here let's pull our equal sign a little bit further down here. We have limit as x tends to 1 of 1 over n x to the n minus 1 natural logarithm of 1 minus x minus limit as x tends to 0 of 1 over n x to the n minus 1 natural logarithm of
1 minus x, and then minus, we can pull this constant out, so we have 1 over n, 0, 1, x n minus 1. The derivative of natural logarithm of 1 minus x is going to be equal to negative 1 over 1 minus x. So looking at this part here, as x tends to 1, we have this area here going to 0. So this goes to 0. And as x tends to 0, this part here goes to 0. So this also goes to 0. What that means is that our integral now becomes to negative 1 over n integral from 0 to 1 of, since we had x minus 1 and we had a negative 1 here, and denominator we have 1 minus x, we can reverse things here a little bit, so we have 1 over n, 0 to 1, 1 minus xn over x to the power n, 1 minus x. So this is a good part that we've gotten to. I would like to just do a sidebar and say, let's imagine a geometrical progression of initial value 1 and common ratio x. So our summation would be something like this. All the way up to xn minus 1, to the n minus 1. So this is 1. And then if we multiply x to that summation, we get x. So x times 1 becomes x, x times x, so we have x squared, x cubed, all the way up to x to the power n. So this is 2. So if we say 1 minus 2, that implies that we have Sn minus xSn being equal to, when we subtract, this cancels with that, this cancels with that, this cancels with that, this cancels with something here. So we have 1 minus xn, meaning that we can now factor out Sn, and we have 1 minus x being equal to, and that means that Sn is equal to 1 minus x over 1 minus x. So this guy here is essentially what we have here. Okay? And Sn is equal to the summation of x to the k from k equals to 1, 0 rather, to k equals to n minus 1. And so let's proceed and say that since our integral in is equals to negative 1 over n times the integral from 0 to 1 of 1 minus x to the n over 1 minus x. And we found that this part here is the same as summation from k equals to 0 to n, or minus 1 of x to the k. we can play around by saying that this is also the same as the summation from k equals to 1 to n of xk to the x of x to the power k minus 1. And the integral of the sum of items is the same as the sum of the integral of independent parts, so we can shift the summation out and the integral in, so that we are now on to the summation from k equals to 1 to n of x to the power k over k from 0 to 1. So In has come to a point where we have negative 1 over n times the summation from k equals to 1 to n of x to the k over k from 0 to 1, and this means that we have not 0, apologies for that, it's 1, summation from k equals to 1 to n of 1 over k. And this comes from, 1 to the k over k minus 0 to the k over k. This goes to 0, and this goes to 1, so we have 1 over k. So this is what led to that. And so since our In is equals to negative this series here is a very famous series, and it's a harmonic series, Hn. So in other words, In is equals to negative Hn, the harmonic series, Hn over n. That is our answer. Okay, so that's the first part, the In. Now we're going to go forward to look at the Jn, the Kn, and the Ln. So let's look at the Jn aspect of the problem. So Jn happens to be the definite integral from x equals to 0 to 1 of x to the power n minus 1, the square of the natural logarithm of 1 minus x. So the first thing we'll do here is go ahead and express this part as the derivative of x to the n minus 1 over n, right? And so using our old integration by parts, v du being equal to uv minus u dv, using this part here, it becomes then 1 over n xn minus 1, the square of that, 0 to 1 minus u dv becomes 1 over that, the derivative of the square of log. Right. So this is the same as limit as x tends to 1 of 1 over n, xn is 1, log square of that, minus limit as x tends to 0, 1 over n, xn minus 1, log x minus 1 over n 0 to 1 xn minus 1, and then this becomes obviously 2 log of 1 minus x negative 1 over 1 minus x. Okay, so what does that become? This goes to 0. It's obvious. And then we can pull this 2 out. And so we have negative 2 over n, 1. And because of this negative, we can flip this around. So we have 1 minus xn over 1 minus x, natural logarithm of 1 minus x. So that's where our problem has come. We know what this guy is. We saw previously that this is the same as the summation from k equals to 1 n of x to the power k minus 1. Okay, so then our problem becomes if we had this, let's just rewrite what we had, xn, sorry, 1 minus xn over 1 minus x, log of 1 minus x. And we say that this guy here is the same as then our integral becomes right, and then we can interchange this integral on the summation side, so we have so this is an interesting integral, right? Because this is the same as I to the k. So our summation of I to the k is important because previously we saw that the summation of, the integral ik or in was essentially the negative harmonic hn, harmonic series hn over n, and that is what exactly we're going to do. So we're going to plug that in. So we have negative hk over k. This negative interact, so we have 2 over n, the summation from k equals to 1 to n of hk over k. And this here is the harmonic series. That we saw previously what it meant. Okay, so what that means for us is that Jn is the same as negative 2 over n, and k equals to 1 to n of ik, which we also saw that could also be represented as positive 2 over n, k equals to 1 of h k over k. Okay, so that is our answer, but we don't want to stop there. We just want to see what is that. Okay, since we know that h of n is the same as h of n is the same as the summation from k equals to 1 to n of 1 over k, then what that means for us, that if we have something like that, that is the same as, let's not use k, let's use I is to 1 to n of 1 over I multiplied by which is the same as summation from I equals to 1 to n, summation from j equals to 1 to n of 1 over I times j. So that's an important step for us. We've the square of hn is the same as ij, and we could say that this is the same as I1 plus I2 plus II plus IN. And so we could focus on this part here and say that this is the same as summing from 1 to n and j from 1 to I of ij plus 1 to n j I plus 1 to n of ij. What if we also say, okay, let's add yeah, so this cancel out, but if we add this to this becomes plus we can now begin from I here to n minus to n over I squared. Okay, so that's important for us. Now what do we do next? If we look at this part, so we can say this is the same as I to 1 n 1 over I j 1 I 1 over j, and this part here is the same as harmonic to the I. right? Plus, let's keep this for now the way it is. Minus, okay. So in other words, this becomes the summation to the n from I equals to 1 of hi over I plus summation from I is equals to 1 to n of j is equals to I to n of ij minus summation I is equals to 1 to n of 1 over I squared. Let's play around a little bit, focusing on this part here, because we'll see that this summation from I equals to 1 to n, summation from j equals to 1, I rather, to n of 1 over ij is just the same as when I equals to 1, we'll see it's 1 over 1 times 1, and it begins from 1, from I equals to 1 to n, so 1 over let's not have that bracket there because that will confuse us. So we have 1 over 1 times n. And then when I equals to 2, we have 1 over 2 times 2, 1 over 2, 3, 1 over 2n. And this goes all the way until we have I of n. Okay. We can rearrange this in a way that we can now begin by saying, what about if we pick 1, and then if we pick 2 out, we have 1. And if we pick 3, we have 1 over 3, 1 over 1 over 2, 1 over 3, and all the way until we see this n here, all the way. So if we bring 1 over n out, we have 1 over 1, 1 over 2, plus 1 over n. What this is telling us is that this is the same as summing from I equals to 1 to n. In other words, this 1, this all the way here. But we're summing because it means that the j begins from 1 up to I. Because at 2 it stops at 2, at 3 it stops at 3, or 1 over ij. So in other words, this guy here is the same as what we have here. And so if our initial problem was we were summing to n hi over I plus the summation from I equals to 1 to n, j equals to I to n minus summation. We see that this is also the same as I equals to 1 to n j equals to 1 to I of 1 over ij which is equal to right. So this is 2, the summation from okay. So in other words, if we had that, and another way of expressing this is hn bracket squared like that. So we can see that 2 hi over I is the same as h squared plus hn that. This is important for us because what we had seen previously was that our problem j of n was equal to 2 over n summation of hk over k from k equals to 1 to n. And now that we know what this part is, this is equals to hn squared plus hn squared. So it means that Jn is equals to the harmonic n, series n, divided by n. And that, ladies and gentlemen, is another expression that we needed. And so we've solved In, we've solved Jn. Now the next phase for us is to look at Kn. To the next integral, k of n, which is equal to the definite integral from x equals to 0 to x equals to 1 of x to n minus 1 natural logarithm of 1 minus x to the power 3. So how do we go about handling this situation? The first thing we'll do is to express this part as a derivative of x to the n minus 1 over n, right? And then we'll go ahead and use integration by parts, which would, if that is an integral of the product of a function v and the derivative of function u, then when you integrate that, you get uv minus u times the derivative of function v. So with that in mind, what do we get? Our uv becomes 1 over n x to the n minus 1 log to the 3 1 minus x 0 1 minus 0 1 times the derivative of right, and this becomes limit as x tends to 1 of 1 over n, x to the n minus 1 log 3 and minus x, minus limit as x tends to 0 of 1 over n, x to the n minus 1 log the 3 1 minus x, minus the integral from 0 to 1 of 1 over that x to the n minus 1, and then we have this guy becomes 3 log 2 negative 1 1 minus x, like that. So what we see here is that this guy goes to 0 because 1 to the n is 1, 1 minus 1 is 0, so this goes to 0, and also this part goes to 0 since log of 1 is 0. And now we can so if those first two items go to 0, so we now have negative 0 to 1, 1 over n, xn minus 1, we have 3 log right. So this here can interact with this, and we can pull the constants out, so we have negative 3 over n 0 1 xn over 1 minus x okay, and we know that this is the same as the summation from k equals to 1 to n of right. So this becomes negative 3 over n 0 1 summation from k equals to 1 to n of okay. And what we see here is we can swap the summation and the integral sign. So we have 3n summation goes to 1 to n 0 1 x 1 log okay, and we see that this part here is the same as j k. Okay, so our integral kn is the same as negative 3 over n summation from k equals to 1 to n of jk, which is the same as hk squared hk that over k. So this is the partial answer, right? But we don't want to stop there. Having this summation thing is a little bit more complex and complicated. So let's use what we call Abel's summation. By parts. What does that say? It means that when you have a product, A, K, B, K, these are items, that exist with indices k or index k, ranging from 1 to infinity, but let's say the product goes up to n, then that is the same as a n b n plus 1 plus the summation of that to n ak bk minus bk plus 1. So where an is the summation of ak terms from k equals to 1 to n. So we're going to use this. Okay. Now, before we even attempt to use the Abel summation by parts, I thought it would be wise to prove it. So here we have a proof. Said at the very top, the summation ak bk from k equals to 1 to n is equals to an bn plus 1 plus summation from k equals to 1 to n of ak bk minus bk plus 1, where an is equals to summation 1 of ak. So we're going to prove that. So we know that an is equals to a1 plus a2 plus all the way up to an. An minus 1 is equals to a1 plus a2 all the way up to small a n minus 1. Therefore, small a n is the same as capital A n minus capital A n minus 1. Important. So that means that our summation from k equals to 1 of n is the same as the summation from k equals to 1 to n. In place of a k we have capital AK minus capital AK minus 1 bk, which is equal to k1 to n capital AK1 bk minus just 1 to n capital AK minus 1 bk. Let's shift the k index here by 1. So this is the same as k equals 0 to n minus 1 ak bk plus 1. So this becomes n k is 1 ak bk minus k1 to n ak bk plus 1, and the 0th term we will just keep subtracting that as 0 b1, and to compensate for the n, since we just added this nth term, we will add an b n plus 1. So we've come to a situation where we have our sum being equal to a0 b1, but this is 0, this goes to 0, so we don't need that, plus an bn plus 1. So we can begin with that first, and so we have an0 bn plus 1 plus combining these two together, so we have ak bk minus bk plus 1, and here we've proved it. So we proved Abel's summation by parts. Okay. However, what our main interest here is to solve for Kn, which is negative 3 over n, summation from k equals to 1 to n of h, the harmonic series, k squared plus that is our interest. And that's what we're going to use the Abel's let me see, I need to correct that part. That part is actually an. So let's see how we can prove or maybe solve this further, simplify this expression further using Abel's summation by parts. Okay, if we take, say, let ak be equal to 1 over k and bk be equal to okay. So what that means is that an is equals to the summation from k equals to 1 to n of 1 over k, which is equals to hn. Okay, so this small exercise is important for us. Then what happens? What happens is that now our summation from k equals to 1 to n of h k squared let's focus on that for now is equals to capital AN is going to be HN, and then Bn plus 1, small bn plus 1 is Hn plus 1 squared plus Hn plus 1 square in brackets. Okay, plus summation from k equals to 1 to n. AK is going to be HK. BK is going to be HK plus HK squared minus bk1 is hk plus 1 squared minus. Let's just do that. Okay. So that we can even expand it and make it more obvious. Okay. So what do? I'm thinking we can focus, or let's reorganize it a little bit more so that it is much obvious. So let's take that. Um, let's, okay, so let's try and focus on this, and then we shall focus on that. What is hk squared minus hk? Not that. So this is the same as summations from I equals to 1 to k of 1 over I squared minus summation I is equals to 1 to k plus 1 of 1 over I squared. So by using the difference of two squares, if you have a minus b squared, that's the same as a minus b, a plus b. Using this, we can say that this is the same as equals to 1 k 1 over I minus summation to k plus 1 I equals to 1 to k plus equals to, this is 1 over I equals to 1 to k plus 1 over I. So we can see here we are left with negative 1 over k plus 1, and here we are left with 2 summation up to k I equals to 1 plus 1 over k plus 1. Now this part here, this part is the same as hk, so this is the same as negative 1 over k plus 1 to hk plus 1 over k plus 1. So meaning that hk squared minus hk plus 1 squared is the same as negative 2 hk over k plus 1 minus k plus 1 squared. Okay, how about hk square in bracket minus hk plus 1 that. That's the same as from I equals to 1 to k of 1 over I squared minus summation from I equals to 1 to k plus 1 of 1 over I squared. So which is the same as over I squared minus equals to 1 to k. Let's just write it like that. And this and that goes, so we're left with negative 1 over k plus 1 squared. So what we do have is now that the summation from k equals to 1 to n of hk squared plus hk that over k, since this was equals to that, plus the summation from k equals to 1 to n of hk this means this is the same as this hk. This part here will take that, which is negative 2hk over k plus 1 minus 1 over k plus 1 squared. And then this part here will take this part, which is negative 1 over k plus 1 squared. Okay, which is equals to hn plus 1 squared, hn plus 1, the square bracket, plus hk negative 2hk over k plus 1, and we have 2 over k plus 1 squared. We can pull the negative 2 out, so we have hn and we multiply across, so we have hk squared plus hk over k plus 1 squared. Okay, so I think that's a lot of progress for now. Let's see how we may progress from there. Okay. One of the things to note is that hk squared is the same as h up to k plus 1 minus 1 over k plus 1 squared. And hk is just the same as h. Okay, so using these substitutions, we can plug it into our equations. Equals to 1 to n of hk plus hk minus 1 over k plus 1. So this is 1. Let me try to delete that. So we have h k plus 1 minus 1 over k plus 1 over k plus 1 squared. Okay. Well, let's proceed and see where that will take us. Let's just restate where we've gotten ourselves to. So we have summation from k equals to 1 to n of the harmonic to the k squared plus the harmonic to k the power 2 over k. And this we've said is equal to the harmonic of n in bracket n plus 1 squared plus n plus 1, that minus 2 summation from k equals to 1 to n, open bracket, harmonic k plus 1 minus 1 over k plus 1 squared over k plus 1 plus harmonic h k plus 1 minus 1 over k plus 1 over k plus 1 squared. So we can expand this part, and that means that let's bring this equal sign here. So we have harmonic to the n plus 1 squared plus 1 squared minus 2 to the 1, and then we have k plus 1 squared 2 harmonic k plus 1 over k plus 1 plus 1 over k plus 1 squared all over k plus 1 plus 1 over k plus 1 squared minus 1 over k plus 1 cubed. Okay, so let's re-express this in a way that is as simplified fractions. So we have hn squared hn plus 1 squared minus 2, and this is from k equals to 1. Now here we have k plus 1 squared over k plus 1 minus hk plus 1 over k plus 1 squared plus 1 over k plus 1 cubic, this and this interacting, plus harmonic k plus 1 over squared minus 1 over k plus 1 cubic. So we see that this interacts with this and this interacts with that. So we come to group to n. We have harmonic k plus 1 squared over k plus 1, and then we have harmonic k plus 1, this and this, over k plus 1 squared, and this would cancel. Okay, so we're going to shift the index here so that we have a simple k. What does that mean? So we have hn plus 1 squared plus hn plus 1 bracket squared minus 2 will begin from k equals to 2 here to n plus 1 hk squared k minus hk over k squared. Okay. And what does that mean? It means we can re-express this part so that it begins from k equals to 1 to n in the following way. So we have hn plus 1 squared plus hn plus 1 bracket squared minus 2 k equals to 1. So we'd have to compensate for when, because we don't have k equals to 1, but we'd have to compensate it for that later. And then we will have to add separately the n plus 1 term. So this is that over k minus hk over k squared. And so what happens eventually is that we have now to factor in the minus 1 term. So let's say we have a bracket there. So what we'll do is we'll have to, and there's that. So for the k equals to 0, equals to 1, we have to subtract that off. So what we do is we subtract 2 h1 squared over 1 minus h1 over 1 squared, and then we have to obviously add hn plus 1 squared over n plus 1 minus hn plus 1 over n plus 1 squared. h1 squared is just going to be 1 over 1, so which is 1, so 1 squared is 1, so these terms cancel. And so what happens for us is that this summation simplifies to the following expression. So let me just begin by writing what we're trying to do here. So we have hk squared plus hk squared over k this is equals to hn plus 1 squared plus hn plus 1 squared minus 2 k is equals to 1 to n hk squared over k minus h k over k squared, and then we'll have 2 hn plus 1 squared over n plus 1 plus 2 hn plus 1 over n plus 1 squared. So we would have to the question is, what is okay, and also that's number 1, and number 2, what is so this is our next exercise, and then after we are able to solve those summation, we can combine everything together. So let's see how that is solved. So we had some big questions previously, and that is we didn't know what that was, and also we didn't know what would be equal to. So I wouldn't really want to focus on this, but let's focus on this one here. Okay, and as usual, would go back to Abel's summation by parts, where if you had a summations from k equals to 1 to n of ak bk, that would be equal to an bn plus 1 plus summation to n from k equals to 1 of ak bk minus bk plus 1, where an is taken to be the summation from k equals to 1 to n of ak, small ak. So we're going to use that. This is going to be our friend. And we've proved that previously. Therefore, if we assume that small ak is equals to 1 over k squared, and bk is equals to the harmonic series k, then therefore the summation from k equals to 1 to n of h k over k squared is equals to capital an is going to be equal to the summation of this, so that is hn to the squared, and bn plus 1 is going to be equal to hn plus 1 plus summation from k equals to 1 to n. ak for us would be hk that, and then bk would be equal to negative 1 over k plus 1. So this becomes hn plus 1 minus the summation from k equals to 1 to n hk over k plus 1. It is same as hn over hn plus 1 minus the summation from k equals to 1 to n hk squared is the same as hk plus 1 squared minus 1 over k plus 1 squared over k plus 1. Okay, and so we can reorganize this second part so that we have hn bracket squared hn plus 1 minus from k equals to 1 to n of hk over 1 over k plus 1 minus 1 over k plus 1 cubic. And then we continue, and here we are still trying to express this. We've come to a point where we have hk plus 1 over k plus 1 minus 1 over k plus 1 cubic. Okay, this is 2 up there. And so let's shift the index here so that we get hn bracket squared hn plus 1 minus 2n plus 1, k starts from 2, and so we do have hk over k, and this that, minus 1 over k cube, and we can now reorganize so that this starts from 1 in such a way that we have plus 1 minus hk Okay, now we have to compensate for this one by doing the following, by subtracting h1 over 1 minus 1 over 1 cubic. And then we have to factor in the n plus 1, so we have plus hn plus 1 squared minus 1 over. Okay, and this is 1, so this is 1, this is 1, so the entire thing goes to 0. And so we come to a point where we have and this minus comes out, so we have minus h plus 1 squared and plus 1 plus 1 over cube. So this becomes hn hn plus 1 minus so 1 to n hk squared over k plus summation from k equals to 1 to n over cube minus hn plus 1 bracket squared n plus 1 plus 1 over cube. This guy here is the same as h to the 3 of n. So in other words, our summation comes to as h n to 3 minus we could just try to delete that so that we create space for what we're about to write. Plus 1 over cube. So we now know what this term is, so let's go back and try to now bunch everything together and see where that leads us to. So previously we had shown that was equal to harmonic to the n minus 2 hk squared over k minus hk over k squared minus 2 hn plus 1 squared over plus 2 squared, and which is the same as plus 2 minus 2 hn plus 1 squared over n plus 1 plus 2 hn plus 1 over n plus 1 squared. So we now know what this guy is, and we're going to plug that in so that we see what it gives us. So let's bring the equal sign here so that we have enough space. Okay, plus 2, and so we have hn plus 1 hn, right, minus n hk squared over k plus hn cube minus hn plus 1 over n plus 1 plus 1 over n plus 1 cubic, and then minus 2 hn plus 1 squared over n plus 1 plus 2 hn plus 1 over n plus 1 squared. Okay, so let's see how to break this down. Go ahead and say we have hn plus 1 squared plus hn plus 1 minus, let's pull this together, so we have 2 hk squared plus hk over k, so this and this are together, and then we have plus 2 hn plus 1 hn squared plus 2 hn to the 3 in brackets minus 2 hn plus 1 plus 2 so we have 2 n plus 1 cubic minus 2 hn plus 1 squared over n plus 1 plus 2 hn plus 1 over n plus 1 squared. Okay. Let's see. What we were able to show in the previous slide is that the summation from k equals to 1 to n of the harmonic to the k squared, harmonic to the k bracket squared over k was equal to harmonic to the n, harmonic to the h n plus 1 squared and 1 bracket squared minus twice the summation from k equals to 1 to n of harmonic to the k squared, harmonic to the k in bracket squared over k plus 2 1 plus twice to the n cube minus twice harmonic n plus 1 bracket squared over n plus 1 plus 2 n plus 1 to the cube minus twice h plus 1 squared over n plus 1 plus twice harmonic to the n plus 1 over n plus 1 squared. Important thing to note is that this part is the same as this part here, and we can bunch them together by taking whatever is on the right hand side to the left hand side, so that we have now thrice of that is equals to harmonic plus 1 squared plus twice n plus 1 plus twice hn cubed minus twice plus twice over n plus 1 cubed minus squared over n plus 1 plus 2 over n plus 1 squared. One thing that's important to note is that since Hn is the same as the summation from k equals to 1 to n over 1 k, what that means for us is that is equals to so, and therefore Hn squared is the same as which is equals to okay. So that is the first thing that we need to note. Then Hn is the same as therefore is equals to which is equals to Hn, sorry. Okay, so we do have this and that defined. And so we're going to now substitute those back into our original equation that we've seen above here, this equation above. Going to substitute in here and then see how that transforms our summation. So if at the very top we have this if that's what we have, And we know that, let's use some color coding, and we know that is equals to h n squared 2h n over n plus 1 squared. At the same time, we know that so we know those to be true. What that means is that in place of this, we're going to have hn squared plus 2hn over n plus 1 plus 1 over n plus 1 squared. And in place of this, we're going to have okay, so that part is done. And in place of this, we have hn plus 1 over n plus 1 hn, and then this remains, so we have twice hn to bracket 3 minus 2. In place of this guy here, we have in brackets hn 2 plus and then here we're going to have 2 over n plus 1 cubed, and then here we have twice hn squared plus hn twice over n plus 1 plus 1 over n plus 1 squared out of n plus 1, and then plus, in place of this last one, we have twice hn plus 1 over n plus 1 over n plus 1 squared. So this becomes hn cube, not bracket, just cube, plus twice hn squared over n plus 1 plus hn over n plus 1 squared plus hn bracket squared plus hn over n plus 1 squared plus, now we are here, we have twice hn squared see whether that is that is not correct, because the correct form is twice hn like that plus twice hn over n plus 1 plus twice hn bracket cube minus let's see. We forgot this, so we need to put n plus 1 there so that we have twice hn over n plus 1 minus twice n plus this and that plus twice n cube, we're here, minus twice hn squared n plus 1 minus 4 hn n plus 1 squared minus 2 n plus 1 cubed, and then we're now here, we have plus twice hn over n plus 1 squared, and then plus twice 1 over n plus 1 cube. Okay, so this is fascinating. So let's begin handling some cancellations here. This and this cancel out, and then this and this cancel out, so we'll just do this. Okay, and then the next item, let me see, this and this and these two would cancel each other. Negative 4 plus 2 remains 2, negative 2, and then these 2, so these end up canceling each other. And then we have this and this also would cancel each other. And lastly, we have this and this cancel each other. So in essence, the things that end up remaining are n to the cube, these hn to the power bracket 2, and this, so we can sum these two to make 3, and then we do have this one here. So in essence, what we have is that the summation from k equals to 1 to n, thrice of that, hk squared h over k is equal to hn cubed plus 3 hn to the power that plus 2 hn that, which means that is equals to a third of so we do have a small pause there, and we're going to use this finding to substitute to the integral, because we saw what the previous integrals were, but now we are interested in finding for kn. What is kn? So let's go back and see what kn was in relation to this summation. So since our integral of interest kn being equal to the integral from x equals to 0 to 1 of x to the power n minus 1 natural log to 3 of 1 minus x. Since we found it to be equal to negative 3 over n summation from k equals to 1 to n, the harmonic to the k squared plus harmonic k up to there, and we already know what this part is, then it means that this is the same as 1 over n harmonic to the n cube plus 3 hn to the 2 plus twice hn. Right. So, and that is what our kn is. Next, we're going to try and see what ln is. And then, obviously, at the end of it all, we'll see what in is, jn is, kn, and finally ln. So, very interesting integrals here. So, let's move on to ln. And we don't really want to dwell so much on this because this is certainly going to take a lot of time, and I would like to dedicate a separate video on that. But ln is x to the n minus 1 times the natural logarithm to the power 4 of 1 minus x. And this part can be expressed as the derivative of x to the n minus 1 over n. Okay. Then we can use now integration by parts, where if we have a product of the function v and the derivative of function u, when you integrate that, you have uv minus u times the derivative of v. So this being our driving function or relation, then it means that we have 0 to 1, 1 over n x to the n minus 1 times the derivative of log to the 4 1 minus x. But before we even go there, I had eliminated a very important step there, and that is the uv part, which is 1 over n x to the n log to the 4 of 1 minus x 0 1. So this is the same as limit as x tends to 1 of 1 n minus 1 log 4 1 minus x minus limit as x tends to 0 of 1 over n x minus 1 log to the 4 1 minus x minus 0 to 1 n x minus 1. The derivative of log 1 minus x to the power 4 is the same as 4 log to the power 3 1 minus x times the derivative of log of 1 minus x, which is negative 1 over 1 minus x. So this negative 1 interacts with this, so that now our next step, we know this goes to 0, this goes to 0, would be that we have 1, let's pull even 4 out, so we have negative 4 over n, 0, 1, and then we have 1 minus x to the n, this negative 1 interacting with x to the n minus 1, 1 minus x log 3 1 minus x. Okay, so since our problem has ln has come to this, rather, let's delete that. It's 1 minus x to the n, 1 minus x log 3 1 minus x dx. And this can be expressed as an arithmetic progression sum. So we have 0 1 summation from k equals to 1 to n of x to the power k minus 1 log 3 1 minus x. So we can interchange the sum and the integration part without losing any generality there. So we have negative 4 over n, not 3, summation k1 to n, 0 to 1 xk minus 1 log 3 1 minus x dx. Now we see that this part here is the same as k, capital K of k. So our sum becomes is equals to negative 4 over n from k equals to 1 n. We saw that to be negative h to the k to the power 3 plus 3 hk hk 2 plus 2 hk divided by k bracket. This negative and this negative would interact, so we have 4n summation from k equals to 1 to n hk to the 3 plus 3 hk hk bracket 2 plus 2 hk bracket 2 over k. Now we could really spend some time to show how we can move to a much simpler relation, but we want to leave that as a subject of another video. But we just want to show that ln is equals to 4, positive 4 over n. K is equals to 1 to the n hk3 plus h3 hk2 plus hk3 over k, which is actually at a future date we will show that, but this is the same as three plus 6 hn to the 4 all over n. So we've not proved that, or we've not shown the steps to that final answer, but we will take that by faith for now. But that is what it is. So we've shown steps that link between in and jn, jn and kn, kn and ln. So thank you so much for holding it there or hanging in there. This has been absolutely long, close to 2 hours of solving these problems. Thank you for locking in. If you haven't subscribed to our channel, we do really encourage you to consider subscribing to our channel. Here at Everyday Mathematics, we just do enjoy solving these very interesting problems. Until next time, bye-bye.